Now let's finish that famous usable problem's first part. Prove it is doable if x is not 1. Right? If it's a rectangle, but not a square.
So you draw a ladder with lots of steps. We had only 2 steps, very small ladder last time. Here you can extend it with as many steps as you want.
Yeah.
So basically, we're trying to see like if making more steps like can increase this bound, because last time I think we stopped at 3 halves and we cannot go any lower.
Right. Last time what we said was 1 plus x squared plus x to the 4th over x plus x cubed is at least 3 halves.
Yeah. So yeah.
Equality when x equals 1.
So this time we make it with 4 steps, and now like by serial computation we have k with a longer expression. So this time when we plug x equals 1, this becomes 5/4, and which is like less than 3 halves. So technically x is not allowed to be equal to 1 because they have to be non-congruent. But when x is really close to 1, you can get really close to 5/4. That's which should be clear. And then we also know that when x gets large, like the numerator clearly like outnumbers the denominator because the numerator has x8 and the denominator has x7. So we can use some like continuity argument because this function is well defined for like all positive x, and it's like also continuous in this range. Therefore, like it should be able to reach any number between 5/4 and above. So what happens between 1 and 5/4? Well, we can add more terms. So for example, if we add more terms like x to 10 plus x to 12.
So now we can go all the way up to 76.
Yes, which is even closer to 1. So for any k, we can like just have enough terms such that like it is smaller than k, and we can find a suitable x for it.
Make x really close to 1.
Yeah.
So then we can also rigorous this if we do some numbers.
Well, if we set up the variables in 2x to the, say, 2a's power, then how do we describe this fraction?
So basically, if we write k to be the sum from a equals 0 to a of x to I over sum from I equals 0 to a minus 1 of x to the 2I plus 1. Right? This fraction is the same one as that one. A is 6. And this fraction is always greater than a plus 1 over a.
Where x is not 0. Oh, not 1.
Where x is, yeah.
When x is
bigger
approaching
than
1. Right.
So as x gets very close to 1, the numerator gets very close to, or the fraction gets very close to a plus 1 over a. And the key idea is, if we want to express any value of k that's strictly greater than 1, we can define a large enough a such that a plus 1 over a is less than, call it like k1 that we want to find. So if I pick k1 to be really, really close to 1, like 1.00001, we can make a really big. Like if we make a 10 million, then it'll work. So that's the key idea here.
And how do we know this is really a decreasing function? What I mean is, you just take one bound, everything has to be more is or covered.
So you're asking why is it that when x increases, k increases?
No, what I'm asking is, can you tell me a more precise okay, putting my question this way. How do you know the range of k right now is actually a plus 1 over a if I only take a terms? Is all the value really covered?
Well, Yannick said that at 1 it's a plus 1 over a.
Right.
It should be continuous, right? Because it's a ratio of two well-behaved functions. And when x is very, very large, your ratio is going to be very, very large.
And also,
Because it's compared term by term.
Yeah.
So at some point it will be as large as you want, so it means it covers all values from 1 to that by continuity.
and this function is increasing.
Yeah.
So when Ivan is saying continuity, he means if you want to actually look at the graph of this function in terms of x. So when x is 1, it's only defined for x, or we're only looking at the part where x is more than 1. So when x is equal to 1, this function reaches some value, this is 1, reaches some value just above 1. So this is a plus 1 over a, that point here. And then the graph starts here, and when x gets really large, the graph is somewhere up here. It's a very high number, right? So since this graph must be a continuous line, or one straight function, there are no jumps in the function or anything, but it's one continuous function, and it goes really high up.
Yeah. The reason you see it's really high up is actually if you throw this first term away, this divide this is basically x, right? So it's more than x, right? So this graph is always lies above the line y equal to x.
Yeah.
Right? So of course it goes to infinity. So basically you are showing from a plus 1 over a, every number is covered, right? So now no matter which k you give me, I will need to find a special a such that a plus 1 over a is less than your k, but more than 1. And after that, using that many terms, I should be okay. Right? There is a value.
And of course, if we can do k can do 1 over k, so we cover k less than 1 as well.
So now the only thing left to talk about is what happens if we want to make a square.
Yeah. And that appears in the next episode.
Next time.
Okay.